How's everything going with your qualifying exam?
Yeah, I just didn't want to hear that, but you asked the answer question.
Maybe, may not. But you don't know what my question is, right? So what's the thermodynamic question?
I didn't solve it, sorry.
It's exactly what we discussed in class, like.
Yeah, two body.
Oh no, I do not give that question. What? I did not give that question. That question.
0 degree, 100 degree, and delta Q equal to each other.
Okay, so you said the practice is very important. The question I give you is like this. Is that possible for you to spontaneously remove energy from low high temperature heat source and to create something with a higher temperature? Is that possible for you to create to reach a temperature higher than the temperature of the high temperature heat source through a spontaneous process? That's my question. Or in other words, is that possible for you to spontaneously remove the energy from low temperature?
I don't think so.
Huh?
Yeah, this question was not in the paper.
No, then this question is so difficult for you guys.
But at least I could write something from.
No, let me ask you a question. So is that possible to do that? Is that possible for you to remove to extract some heat from low temperature heat source and to the high temperature heat source through a spontaneous process?
I think, like, well, you said something about there are 3 different heat sources.
Yeah. If you have 3, yes, you can.
Oh,
Okay. So I give them an answer. So if you have 2 heat sources, no, it's possible. But if you have 3, yes, you can. So I just talked with you. So think about it. You have the fire plant, okay, fire electronic plant. You burn the coals or like the oils to generate the steam and power the generator, correct? So the temperature what's the temperature of the boiling oil called? Probably at most 100 degrees Celsius, right? And then you're driven up engine, okay, the generator to give the electricity. Correct, everybody? And then it's cooled down to room temperature. Okay? So what do you can use for the electricity? Can you use the electricity to power a light bulb? You can, right? So what's the temperature of the light bulb? It's over 3,000 degrees Celsius. That process spontaneously happens. Okay. Of course, you need to burn it first. So it's possible, okay? But if you have 2 sources, no, it's impossible. But if you have 3, yes. But if you can do some calculation, the entropy of the entire process will increase. That's the question I give.
Did you have us calculate the entropy?
Yeah, it's pretty simple.
Oh my god, I could have just write second law of thermodynamics and I could get some marks.
I think if I give the question, that wasn't passed. That's the reason probably select the simpler one. We have 2 professors give the questions. Okay?
They took 2 body interaction.
But that's easier, right?
Yeah, that was easier, but I didn't get time.
Okay, it seems like I'm the bad guy. You give it
Oh my God.
Actually, I think we probably would have liked that question over some other ones that were on that.
Okay, so today I have some draft jobs. Okay, let me what's going on? Why? Today is what? Today. You pen down the work.
Oh, my pen works.
Okay. What about other questions?
Oh my god.
No. The not marker pen, just like regular pen.
Oh.
What about other questions? You know, qualify. What about other?
Yeah, like we had like mechanical questions as well.
Mechanical question. What do you mean?
Yeah, like 2 cams of fabrication process. One broke in between of the fabrication, other went the final stage. 2 cans. So they asked to draw the stress strain curve for that, and then they asked to design a can which can rupture before explode.
Oh yeah, on the Southwest flight.
Huh?
I said on the Southwest flight.
Yeah.
Okay. Anyway, forget about it. Let's talk about this. Okay. So I bring all my materials. I mean, if your class note is thinner than that one, probably you are not collect what I'm talking.
What?
This is my teaching note. If your note is thinner than what I have, that means you did not follow what I'm talking about in your class, okay? So this is all what you're going to cover in your midterm.
Oh, we got a copy of that?
No. Okay, that
Why
means,
did you bring?
Why would you?
because I want to review the entire, I want to have you review the process.
Okay,
Okay.
thank you.
To go through it and to tell you what's the most important part to help you to review it. Because next will not be here, but you're going to take the final the midterm, right? But I have no idea whether I go through it this time or next time, but definitely we need to go through it this week. Okay, because next Monday or Tuesday I'm going to announce the midterm, okay? Why everybody have a sad face? Take it easy.
Who feels good when they know a hurricane is coming, right? Unless you are working in a
I mean,
university, right?
if the hurricane's coming, it's good. You can just stay in your apartment and do the
Exactly,
midterm.
see? That
All right,
kind of-
anyway, let's go back on the class, okay? First of all, let's talk something about homework too, okay? I think everybody submit homework too. So basically, the main purpose of the homework too is just to do the Maxwell relationship and do some calculations, kind of like the transform different kind of the independent variables. So that's the main purpose. The first question, so review the content of the stated thermodynamics and answer the question I give in the class. I think for you guys it should be fine, right? But a lot of people have difficulty on the online students. Okay, basically the first question is about how to derive to measure that one, right? So from the partition function, the question is that if I know the partition function of the ideal gas, how do you calculate the entropy of it? Okay, that's the question. So I think that you have on your note. So the reason why I leave the first question in that way is that I force you guys to see the video or review your class note. You need to find that, okay? But it turned out that somebody cannot find it, especially the online students. Just tell them you review. But I did not make the global announcement to tell you what it is. That means if you see the video clearly, or if you are in class, follow what my instruction very closely, you know what I'm talking about. And if not, go back to video, check. You need to go through the entire video to find it out. That's the way for me to encourage all students. The second one, this is pretty straightforward, right? Calculate the entropy change. We use that quite often when we talk about solutions. You just XA log XA plus XP log XP times RT. That's the derive the Maxwell relationship. That's we already mentioned in the class, right? So it's pretty straightforward. So we just have the four very important thermodynamic functions: energy, enthalpy, Gibbs free energy, Helmholtz, Helmholtz or Helmholtz? Helmholtz. My brain not working that way. Free energy. So okay, by using that kind of the differential form of that kind of four functions, you will get all the Maxwell relationship. Okay.
So I have a question. Like, if there is any function, right, which actually follows which depends on two independent variables of thermodynamics, right? Then we can write it in Maxwell's form, right? We can.
Maxwell function doesn't tell you all the possible relationships. Okay. It only tells you four. You only have four Maxwell
So
relationships.
it's for only those four.
Yeah. Yeah.
So we cannot apply it like.
No. You only have. Why so got disappointed? Even I have hundreds of them, you have difficult to memorize them, trust me. Okay? Anyway, so then we're going to solve this problem. Okay? So the fourth question probably has some difficulty, but there's nothing about thermodynamics. It still is like a mathematical trick. Okay, but I want you to go through this process. Basically, we need to do 2 times of the independent parameter change.
Before you even start the fourth one, are there multiple ways to do it?
Yeah, there's multiple ways.
Okay, I just want to make sure. Like,
Yeah. As long as you get the final result, fine. Okay. And honest with you, I also put this one to Gemini, and they also give me different ways to do it. And always correct. So if you jump into the Gemini, it's fine. But I will make sure something show up in your qualify next time. Is that closed book in class exam?
Which one? What is it?
See that I'm more gentle than the department. Okay, so The question, the first question is asking you guys to verify this equation to show this one. Okay? This is what we want to do, right? So you can see that this basically with this claim is like show for the simple PV system. That means the system have two independent parameters P and V. It's not necessary to be ideal gas, okay? Not necessary to be ideal gas, okay? It can be liquid, it can be solid, it can be any kind of actual or real gas. Doesn't matter, okay? As long as it's a PV system. PV system means what? PV system means that the delta W equals to PdV, okay? So this is the PV system, okay? Of course, we have some other such systems. For example, electric, okay? The power of the power generated by electricity cannot be expressed in that way, right? So then for the electricity system, we cannot use this equation to express it, okay? But for this one, yes, we can. Okay, so what do we know? We only know CP, right? Okay, CP is what? I show one way, okay? If you have other way, you can do the drama as well, okay? So we know that the CP is what? Is partial H, partial T. Correct? I mean, the same thing, the CV is what? Is partial U, partial T. Right? You can use any kind of region. We can start from this one, okay? If you start with CV, that also works, okay? Doesn't matter, okay? So you can, if you see that if I write this kind of the partial differentiation in such a way, that means we automatically select T and P as independent variable. Correct, everybody? And of course, what's the, but you can see that we have CV here, right? So if we want to calculate CV, we know that it should be derived something from the internal energy, right? So we want to express the entropy in terms of the internal energy, so it should be something like this. Correct? Right? We use the T and P as the independent variable. And the internal energy is the same thing. We use T and T as the independent variable, and T and P as well. Okay? So far so good, right? So we can do the draw. It's partial H, partial T, P equals to what? Equals to the partial U, partial T as constant P plus. Okay, since the P is the independent variable and the P is constant, then we do not need to consider the derivative on this term. We only consider the derivative on V, right? That is partial V, partial T times P. Correct? Right? That's the derivative. Correct, everybody? All right. So, and then first of all, let's think about this term. Okay? Partial U, partial T appears. Correct, everybody? But if we want to see the CV is what? It's partial U, partial T, V, right? But here is a partial U, partial T, right? We still need to change, okay? For that one, we know that if we do the partial derivative at function of T with a constant V, actually we are selecting TV as the independent variable. But for this case, we're using TT as independent variable, right? So we can do some transformation. We just is not transformation. We just introduce some intermediate variable. Okay. We can write U in that term, right? U is function of T and V. V is further function of P and T. And in total, U is function of P and P. Correct, everybody? We just introduce the V as an intermediate. Okay. And then we can calculate something like this. So partial U, partial T, constant P equals to, we do this one. We do the partial U, partial T as constant V first, and then partial U, partial V as constant T, but the V is also a function of P and T, right? And then this is partial V, partial T. Correct? If we introduce this term, we need to have this term like this, right? And you can see that this one shows up. This one is CV. right? Okay. Let me check whether it's right or not. Okay. Any questions? Yeah, go ahead.
Could you explain again why the equation for this?
Why we need to do the equation? The reason is, if we want to find the relation between CP and CV, we know the CV is defined in such a way, right? So you can see that it's a partial derivative on U as a function of t with a constant v. That means in this case, p and v are independent variables, right? But look at this equation, t and p are independent variables, right? So how can we find the relationship between this term and this term? Actually, the way that we introduce the v as a function of pt as an intermediate function, okay? So you can see u is a function of t and v, but v is further a function of t and t, right? So basically, this one is just equals to u tp, right? And then the partial u partial t with constant p is we need to do then we need to do the derivative on this term first, and do the derivative on this first, and then further the v, right? We need to do this kind of derivative in this kind of step, right? So that's the reason how this kind of relation, right? And then by doing that, we can see that CV appears, right? So we put this equation back to here. So then this one equals to CP actually equals to CV plus partial U partial V T and partial V partial T P. Okay? And plus partial V partial T P times P. Okay, this is what we have. So we can just put it here on this side, move to the left side of the equal sign, and this one equals to. Correct, everybody? And then, of course, this one equals to partial V, partial T, P plus partial U, partial V. Correct? Is that correct, everybody? Actually, if you check the textbook just did the work to this step. Okay, you can already find a lot of interesting solutions. I mean, interesting things. But we can move further. Okay, we can move further. So remember here, U is partial U, partial V, T. Right? We have this term here, right? So if I read this one in this way, if I read the partial derivative of U as function of V as a constant T, that means what? That means actually I'm selecting V and T as an independent variable for the U, correct? For the internal energy. Correct, everybody? But we know this relationship. Correct? We only know this relationship, right? So for this relationship, U is a function of S and V. Okay? It's not a function of U and T, V and T. It's a V and S. Correct, everybody? So how can we further exchange? The same thing, basically the same story or same strategy. Function of T, okay, it's not function of the, it's function of entropy, and entropy is further a function of V and T, okay? And this one is also T, right? Sorry, this one is V, okay? Got it? So it's a V. U as a function S and V, and S is further function of V and T. So if I expand that way, so U eventually become a function of V and T, correct? I use the entropy as an intermediate. So if I have this one, so the partial U, partial V, T will equals to partial U, partial V, S, okay? and plus partial u partial s v times partial s partial v and t. Correct? Basically, we are doing the same thing the second time. Correct? Okay, what's the partial u partial vs? Partial u partial vs. Partial u partial vs is t. Okay? Oh no. Partial u partial v as a constant s is minus p. Negative p. Correct, everybody? And the partial u partial s at constant v, partial u partial s at constant v is the p. Right? It's the temperature times the partial s partial v. Okay? So that one, check the Maxwell relationship. So what's the Maxwell relationship gives us? The Maxwell relationship tells us the Maxwell relationship tells us partial s partial v constant t equals to
This d t constant e, right?
partial
You can
t
interchange it, right?
partial t. Right? Put it here. Okay. So eventually we have the first term going to change. Okay. And the p, we have the p. Okay. And this term equals to that much minus p plus t times, use the Maxwell equation, the partial p, partial t, v. Okay? And these two terms cancel. And eventually you get what we have. Right?
That part is here, right?
Is that correct, everybody? So that's why we spent so much time to derive this one. Okay, let me first of all, but my purpose is to ask you to practice this kind of process. Okay, we just change the independent variable. How can we change the independent variable when we solve the problems? Okay. Practically speaking. Okay. So the CP is definition. The CP is defined in this way, right? The CP is defined in that way. Okay, and the CV is defined in that way. Correct, everybody? So if we want to measure them experimentally, we need to know the entropy change, we need to know the internal energy change. But it's really hard to measure. Right? It's really hard for us to measure the energy. Because first of all, energy is relative. Okay, it's relative. We don't have it depends on which reference point you're choosing. The other thing is that if you want to measure it, you need to know how much work is performed, how much heat is got exchanged.
Sorry, I didn't. So how foundational is this, like, impossibility of measurement for entropy? Is
You
that,
can measure.
Okay, so someday we'll
It's
be
more
able to
complicated.
measure it. Okay.
It's simply very complicated.
Okay.
Okay? You can measure it, but it's complicated, okay? But the question is, if there are kind of alternative way for us to do the job. So you can see that by doing all this transformation, it just becomes measurement of pressure, temperature, volume. More convenient for us to do the measurement. Correct, everybody? But we still have a way to measure the entropy and internal energy, but how can we measure the entropy? It's really hard. Right? We have no experimental way to measure it directly. We can calculate, but we have no way to measure it directly. So whenever you have the entropy flow in your expression, we will try our best to find an alternative way to change this expression with some other measurable parameters. Okay, that's why, as I mentioned when we introduced the Maxwell relationship, that's one main purpose. Okay, which replace the expression include entropy with other parameters.
Can you explain the line equals negative p plus t, all that between those two lines, how you got there?
You mean from this one to this one?
Yeah.
See this one. We know that the du equals to dds minus pdv. Correct, everybody? So then from that one, the partial u, partial v, I constant s. This one, not the p. Correct? correct? From this one, I mean also partial u, partial s. The function v, this one equals to t. Okay, you put this two back to here, you get this expression. Right? Clear? Mathematical trick. But of course, you can also find the alternative way to do the same thing, okay? But the procedure is the same. The procedure is the same, but you can choose different route. Okay, for here we use this definition. Okay, we use this definition to do the calculation, no problem. You can also use this one to do the job. It's the t, partial s, partial t, p. Okay, and cv equals to t, partial s, partial t, v. You can also use this relationship to derive, okay? And you will find that you can reach this conclusion as well. Okay? Just have a try. If you cannot find an answer, just dump this question to ChatGPT or not ChatGPT. Gemini, they can give you an answer. Okay, so the next one is, actually the next question is even simpler. Okay, so question 5 is even simpler. So it's asking us to do this job. Okay, to do this job. So it's just practice, okay? Still the same thing. So it's change. I mean, this equation measures how the constant volume thermal capacitance changes as a function of the volume, right? So it tells us instead of directly measure the change of the thermal of the heat capacitance, we can measure from the change of the pressure as the second order derivative of pressure as a function of T. Okay? But we know that for the ideal gas, the P, second order derivative of P as a function of T just equals to what? Equals 0. Right? That means it doesn't change. Right? That is for ideal gas. But for real gas or other system, not necessary. Okay? Not that true. So we have this more generalized relationship. How to do that job? The same thing. For that one, we can use this one relation. Okay? T is T, partial S, partial T. V. Okay, we use this definition. This one is easier. This one is easier. Okay. Okay. So then we need to do is the partial C, partial V, constant T. Okay. We have two way here is T, and this one is T. This one is V. Okay. It's constant T, so we don't need to consider the derivative on the T this term. Okay, because it's constant. Okay. Then it's become T times partial V, and then partial S, partial T is V, and this term is what? This one is T. Correct, everybody? Okay. And then, because we assume that S is a continuous function everywhere, okay? There's no abrupt change. In other words, we can swap the order of the differential, right? Become T, okay? Be very careful, partial T, okay? And then this is partial V, S, okay? And then partial V as a constant temperature, right? Partial V as constant temperature, and partial T as constant V, right? Something like this. So we change the order of the derivative, we also change the order of the invariable, in the parameter, okay? What about this term? From the Maxwell equation, we know that partial S, partial V, constant T equals to what? Equals to partial P, partial T, V. Right? Is that right?
Yeah.
So we put this one in. So it becomes T, partial T, partial T. And this one is V, this one also V. Correct? Then this one becomes T times partial. just run in that way, okay? Because for both of the derivatives at a constant. Okay. That's it. Simple. For the same thing, for the CP, partial P, okay, P. You follow the same thing, okay? You just this one equals to negative partial square V, partial T squared, okay? Basically, use this definition, Cp equals to T times partial S, partial T, and that comes P. You can use that starting from this point, follow the same procedure you'll get. That's the basically, last question. Do I need to,
I was just gonna ask if you could, what's this describing physically?
was it describing physically?
Yeah.
Good question. I don't know. I mean, basically, it's just like, as I mentioned, it just tells us, it really depends on the systems, you know what I'm saying? It really depends on systems. So we cannot give a very unified, generalized explanation across all the systems. But mathematically speaking, it just tells us a way how to measure the variation of the heat capacity as a function of heat. The same thing, okay? So it's just that all the systems follow this relationship. So instead of measure the heat capacitance, you can measure the second order PT to measure this variation, okay? Just like this equation, okay? So what's the physical meaning of this equation? It's really hard to explain. So the variation of the entropy as a function of P equals to the pressure as a function of P. It's really hard, but we know that mathematically correct.
So it's just like there is ways to calculate that using
It's a way
some
to calculate
experiment, but this is easy because we can just derivate it like
Yeah.
partially. We can perform PD and get it easily, right?
You can think
So
of it.
it's a mathematical class basically.
It's a good for calculating but not understanding.
Yeah, exactly. You can consider it that way. Okay. Let's go back to the physical science. Last question. So we know that the question is that we know the equilibrium, right? This relationship. We mentioned this one in the class, right? Did we mention this one in the class? I think so.
Yeah, we
This
did.
one
Total derivative?
is total derivative because it's under equilibrium condition. Okay, this is in a phase diagram. This one is in a phase diagram. Okay, we talked about the water. The question is about the water, right? The water has phase diagram. Looks like which one? What's the phase diagram of water? What the water phase diagram looks like? Thank you very much. No, that's not right.
Oh, well, I'm just remembering the example in class
Yeah.
that you gave us for it.
It's probably something like, I forgot. This is the water.
No.
No?
That's
Yeah.
right.
Yeah,
That's
yeah,
what I'm
yeah,
trying.
it's right, it's right.
No, you have a
It's
king
kind
there.
of right, yeah.
You have a king there.
Triple, okay.
It's fine.
I think you shouldn't have the downward slope pointing your.
Yeah, I know.
It doesn't, it doesn't,
It's
okay?
for-
That's the,
for education.
or something like this. This is P, this is T. Okay? Anyway, doesn't matter. Let's not talk about that.
You killed me.
So we're talking about,
Yesterday,
You killed
in the morning.
no, I didn't kill you, anybody. We're talking about this one, okay? So look at it. So it tells us what? It tells us that the, what's the question was?
Explain why ice gets slippery.
Yeah, why ice is slippery? What's the reason for that? The reason is like this, okay? So you can see that the from this one, we know that the dP and T under equilibrium will have negative slope, right? And then this is negative slope, correct, everybody? And we know that the entropy change, that means this one divided by this one is lower than 0, okay? We know that from the liquid to solid, the entropy change is what? Let's put the other way. From solid to liquid, okay? the delta S is what?
Positive.
Is plus, is positive, right? Then from this relationship, we know that from solid to liquid, the volume is smaller than 0. Okay? That means the water is different. That means when it's liquefied, the volume shrinks. When it's solidified, the volume expand. You can do experiment, okay? Just freeze a bowl of water, the volume can expand. It's very counterintuitive, right? But it's the truth, okay? What's the reason for that? The reason is that we have a very special molecule structure, okay? You have a hydrogen bond, whatever. Okay, because this has this shape, this has this shape, okay? Then if the energy in the water condition, you can just, this kind of the small arm can go into this part, okay? But when it's solidified, it always form this kind of structure.
Excuse me, Professor. I want to ask, clarify one thing. Like you talked about negative,
Yeah.
right? Why did you mention that? Why? Negative.
Because this one have this two relationship.
Uh-huh.
Okay. So dp dt is negative. Then we have this one negative,
So
right?
that's a slope, that equation.
Yeah, this is slope. This equation
Yeah,
is
so if
actually
it
minus
is
slope.
negative, that means it will be negative that side, right?
That means the slope is negative.
Yeah.
Okay.
Okay. And for the, if the positive on the liquid and solid boundary should look like something like this.
Okay.
Okay. I think I draw something wrong. Sorry about it. I think it should be this. Right? Sorry about that. Right? So if it's negative, okay, it looks like the positive looks like this. Right? Got my point? So if it's negative, look at if it's negative, and from this relation we know that the entropy from solid to liquid always increase, right? But from this relation, if the slope is negative, we also know that you should know the change of the volume is negative. That means what? That means if you have a piece of ice, you compress it, it's liquefied. Okay? It's different from other systems. For most of the liquid, if you compress it, it's solidified. But for ice, if you compress it, it's liquefied. That means if I put pressure on it, ice becomes water. Okay? That's the reason why the ice is very slippery, because you put a body on it, it's melt. Okay, you have some liquid film on the interface. That's the reason it becomes slippery. Okay? Any questions?
So
So essentially the answer is you step on ice and
You melt it.
you melt it.
Yeah, you melt it.
yeah, so if it is not water case, if it's
If that's a different story.
so
if you
so
dry
those-
ice, for example, if
those
you
curve will be like this, positive.
yeah, if for example, if it's dry ice, you step on it, it's not slippery. Right?
It will.
It's
actually opposite.
become denser. Okay. If you dry ice, you step on it, it doesn't melt. Okay.
Okay, but let's say there, in the refrigerator there is ice, right? So when we actually get the ice, right, it sticks on our hands, right?
Yes. This is because the sweat on the surface of your skin got
Solid
frozen.
Okay.
Okay, but if you try your part
Grab it.
to press it, it's going to liquefy. You can do this job, okay? Try doing something like this. Go back home, find a piece of ice, okay? And find a piece of rope, okay? Something with very low thermal conductivity. I mean, thermal conductivity and thermal capacity and heat capacity. Okay? Also freeze it. Piece of ice bar and put the rope on this way. Try to drag it, and you can cut the ice in. You will not cut the ice to two pieces, but eventually you will find that the rope will go through the ice, but ice still ice bar.
And it's not because it's warmer.
But that?
It's not because it's warmer, it's because of the pressure.
Yeah.
So like if the
it's
rope,
not. Yeah, exactly.
if like the rope you used was at 32 degrees or
Yeah, exactly. That's the reason you need to make sure that rope is in the same temperature. Otherwise, people may argue that because it's warmer. You know what I'm saying? Or do not use metal, because people will argue, well, metal has really high thermal conductivity. That is not the case. It's just because of pressure.
But if the rope is colder than the
The same thing. The same thing. If the pressure, but you cannot be ultra cold. Okay, you cannot be that very, very cold, because eventually this bar doesn't. I mean, it's probably also go to positive. For example, you know that the ice exists on the bottom of the ocean, because this one doesn't go unlimited high. Right? When the pressure is very high, you still solidify it. Okay. So that only in this some very local area. So that means if you have water, if you have ice, you compress it, it becomes water. But if you further compress, it comes back to the solid. Okay, it comes back to solid.
So it is, water is the exceptional case.
It's one exception. It's very rare. I mean, yes.
So is there any similar kind of thing?
I don't know. You can check online to see whether something has the similar effect of water. Okay. I guess they are pretty much about homework too. Once again, for the midterm, we're going to cover everything before the phase diagram, okay? Before the phase diagram. That means we're going to cover the first and second law of thermodynamics. Forget about third law, okay? I'm not going to test it, okay? First and second law. I mean, more specifically for the second law, we're going to talk something about the Carnot circle and how to calculate the entropy. I mean, we're going to touch a little bit about statistics, but not too much, okay? The reason I introduced the statistics just to tell you, the main purpose it tells you was the explanation of the entropy. But other than that, it's not very, very important for you to understand the thermodynamic processes, okay? And then we talk about the fundamental equations, like as I mentioned, entropy, enthalpy, the enthalpy, internal free energy, Gibbs free energy, something like that. And then we talk about the phase equilibrium, okay? Under the phase equilibrium, I mean, for the closed system, we have temperature, pressure, but for open system, we also need to consider the chemical potential. And then we move on to the mixture of the ideal gas, right? And we and after that, we talk about from the mixture of ideal gas, we introduce the change of the entropy, okay? And also introduce the concept of partial pressure. And then we talk about the actual gas, okay? We introduce the concept of the van der Waals equation, right? And after that, we talk about solutions, right? I mean, basically we start considering interactions. And then we have the concept of the ideal solution, non-ideal solution, and irregular solution. Basically, that's a little bit going to cover for the midterm, okay? And I think next time I will help you to go through this one to give you more details, okay? But for that time, for this class, I think probably still continue about phase diagram because I don't want to give you the interview first, and next time I go back to the phase diagram jumping several times and just make everybody very confusing, right? But I will continue to talk about phase diagram next time to help you to review the class, okay? And where did we stop last time? We talked about the phase diagram. We talked about the miscibility gap, and we also talked about the spin-nodal process, right? And I also mentioned how can we generate the phase diagram. How can we generate the phase diagram from the basically, we're talking about why the unmixing happens, right? Because when the temperature going down, the entropy terms start to, the entropy change become dominant, right? And entropy change is positive, right? That means the two components prefer to repel each other, right? And then we have this kind of shape of the total Gibbs free energy. Okay, we have a bump in the middle, okay? And it goes up, it becomes convex, okay? And then by do this kind of tangent line that the tangent both points, we know this is in the middle, this is miscibility gap, okay? As the temperature changes, you know that the miscibility gap becomes larger and larger, right? And eventually we have this phase diagram, okay? This is temperature, this is A and B, and we have a dome here, right? And inside we call it the miscibility gap. Right, and depends on whether this kind of phase separation or like unmixing is stable or not. We also have some, we call it the spin-nodal process. And inside it, the unmixing will happen spontaneously. And outside, in this range, we call it the spin-nodal decomposition or spin-nodal process. That will happen spontaneously. And on outside areas, this one is metastable process. Okay, metastable process, that means we need to have the nucleoside to lower the energy barrier to make this kind of the phase separation happen, okay? But we're not going to talk too much about the nuclear process or diffusion phase transformation in this class. Okay. So it's a job of the phase transformation class. I'm going to teach a phase transformation next semester. Okay. And you're more than welcome to graduate. It's a selective class, so there's no the same thing. No homework. Just presentation. Happy? And for the presentation, everybody bring their own food. Last semester, I only had one student. And he's online student. And he taught 30 years. But I find that class have a lot of overlap with this one. Okay? But still, if you want, you can graduate. That means you don't need to come to the entire class. Okay? You don't need to come to it because I will spend about 1/3 of the semester to review the entire thermodynamics, just in case some student did not join this class because we have quite a lot of online students. Okay? So I need to. But that means for the first 1/3, 4/3 of the semester, you even do not need to show up because I just repeating what I'm talking about. Easy class. You are more than welcome to graduate. As long as you do not make, as long as you're okay, you do not make some very serious mistake in the class. For example, you just stand up, okay, hopefully you're very stupid. Okay, you fail the class, okay? But otherwise, you should be okay. Okay, so the reason why I introduced this at the beginning, the key concept is, whenever you see this kind of this shape, we have the phase separation or a mixing, okay? And then the unstable area is defined by these two tangent points, okay? That's what we need to know, okay? So we're going to talk about more complicated cases, okay? We're going to talk about more complicated cases. For that one, it's only the solution. We are talking about the unmixing of the solution, right? We only have a single phase, solid phase or liquid phase. Correct, everybody? Basically solid phase. So we want to make the job more complicated, okay? So we start to introduce the phase diagram. Phase diagram. Okay, phase diagram. The first one, we're going to introduce the simplest one, okay? In the textbook, it's called the length diagram. That is the simplest phase diagram. So it looks like, we know that, for example, we know that for the ideal case, the delta H is lower than zero, right, after mixing. That means the solution is stable, right? That means the solution always stable, right? Because, I mean, the two kind of atoms prefer to stay with each other. They're attractive to each other, okay? And this delta H is negative for both liquid and solid. Okay? If the delta is smaller than zero for both liquid and solid, then what will happen? Okay, for example, this is the liquid phase, okay? This is the liquid. This is the liquid, okay? This is the G, okay? GM, okay? This one is liquid. Okay? Any question? No question. This is very normal. Okay? We already measured this sometimes. But for the delta S effect, that one always looks like this, right? And then, at high temperature, we also have the solid phase. We also have the solid, for example, like this curve, okay? This one is the liquid, this one is solid, okay? And at high temperature, we know that we know that G is what? Delta G is the delta H minus T plus, yes. Correct, everybody? At the same temperature, we know that for the liquid, then the G simply equals to this. We know that at the high temperature, when the temperature is high, We know that the entropy of the liquid is larger than the entropy of the solid. Correct, everybody? Is that right? Okay, at high temperature. At high temperature. So this term will dominate. Correct, everybody? This term dominates. It's lower the entire Gibbs free energy. Correct? But when temperature going down, this part becomes less and less dominant, right? Correct, everybody? And then this curve moves up. Correct? We just assume the solid doesn't change that much, okay? And this one goes up. But also, of course, the solid going up as well. However, since the solid has less, has smaller entropy, this one moves up slower than this one, right? Correct, everybody? And eventually, you will have something like this. But anyway, so at the high temperature, it looks like this, right? That means the liquid is a stable state, right? And then when temperature goes up, we just, this one is solid, okay? And eventually, the liquid will go here. Okay? This one is liquid, this one is solid. Correct, everybody? Got that points? And then you can see that follow the same principle. If we have the mixture staying somewhere here, it's become unstable, right? It's preferred to become a mixture of the liquid and solid in order to lower the total Gibbs free energy.
I didn't get that part. Liquid, how it moved up?
Because when the temperature going down, this is negative, right? Maybe this curve looks like this, right? When the T becomes lower, this term becomes smaller, right? Then the negative becomes smaller, then all the curve going up, right? This T is higher, this T is lower, correct? When we keep cooling down, the Gibbs free energy will keep moving up, right?
But it's not liquid anymore.
It depends whether you have the free energy, Gibbs free energy of solid here. If you start to cross the solid one, you start to solidify.
So it actually represents the slow cooling process of the, okay.
Let me redraw it. Okay? The reason I'm redrawing is not because I'm drawing wrong, because I'm so short. Okay, I cannot move it.
So the temperature has to decrease for the entropy to go up, and the liquid that was once stable is now at a higher.
Assume that we have the liquid. We have this is solid, okay? This is solid Gibbs free energy. And the liquid Gibbs free energy is here. And liquid is here. Okay? You can see that if we have some mixture here, this one, we know that the liquid is always stable. Correct? Liquid always stable. Correct, everybody? And when we cool it down, we know that liquid curves start to move up. Right? Start to move up. Of course, solid also move up, but it's move up slower because the entropy of the solid is lower, is smaller, right? This one. Then we just set this point as a constant, as a reference point. Okay? We do not change that curve. Okay? We only analyze the relative motion. Okay? When temperature cooling down, we have something looks like this, right? And this is the critical point. Okay? At this point, it's still stable, right? Still liquid is stable, right? And then, when we further cool down, you can see that these two curves start to cross each other. Correct, everybody? And assume that you originally have this one, okay? Right now, you know that liquid is not a stable state anymore, right? Instead, we just go somewhere here. But are you sure that this solid is a stable state? Not necessary, right? It's not necessary because the same thing. If let me magnify this area, okay? Let me magnify this area, okay? So for example, this is liquid, this is solid. So of course, you all become solid. You lower the total Gibbs free energy of the system. Correct, everybody? But that's not the lowest point. Consider we have the tangent line here. Just we have the tangent line here. Just as was mentioned for the for this kind of unmixing system. So if I become a mixture between solid and liquid, the Gibbs free energy is even lower. Correct, everybody? Become even lower. That means in this area, the liquid is not stable anymore. In this area, in this range, the liquid is not stable anymore. Instead, it's become a mixture of solid and liquid. Right? Become a mixture of solid and liquid. Correct? And you can see, right now we have this area. I draw something like this. This is A, this is B, and this is the temperature, okay? And at this temperature, this area become a liquid and solid mixture, right? And in this range, it's still liquid. Correct, everybody? Okay, if I keep cooling down, this one further move up, right? This curve further moving up. And then this area, the mixture area become here and here, correct? Defined by these two tangent points. And then we still do the same thing. We project these two here, okay? This is another temperature. And we know this area is the liquid plus a solid. And this area is just a liquid, correct? This area is a liquid. Right? And this area is what? It's solid, right? Because you can see that, hold on. Did I make some mistake? No. This one is, which one is solid? This one is solid. Which one then? This one is solid. This one is liquid, right? So you can see on this area, still liquid is stable. But on this area, we only have solids are stable, right? And in between is solid and plus liquid are stable. I more preferred. I mean, I prefer by the deep spring energy, right? And we further move it up. We move it up further. We move it through here, right? This one is a solid. This one is liquid. Okay. And then you can see that this between this tangent point and this component are the mixture, right? So we see the same thing. We project here. We project it here. Project it here. And the lower temperature. And then you can see this area are the mixture of the solid and liquid. And this one is liquid, this one is solid. Okay? Eventually, if you connect all this stone together, we have something that looks like this. Okay? We have something that looks like this. To redraw the diagram, this is A, this is B, this is the T. Okay? Eventually, we have something like this. Okay? This one is a liquid. This one is liquid plus solid. This one is solid. Okay? That means what? That means if you have alloy or the solution, when you cool it down, typically, we do not cool it down simultaneously. That means you have a solid piece, something called a solid piece. You know what I'm saying? Basically, we have some solidified, part in the mixture first. Okay? And then part is solid, part is liquid. And when you continue to cool down, everything becomes liquid. And in between is a mixture. Okay, the region of this kind of mixture zone looks like a lens. Okay? Looks like an optical lens. That's the reason we call it this lens diagram. Is that clear? Okay.
So given the point in that lens region, do we know exactly how many percentage of
you know.
A and B
Yeah.
are in which?
That one is called the lever law. Okay. So for example, you have it here. Okay. You cool it down. For example, to this temperature. Okay.
Yeah, no, I mean like,
I know. You cool it down to this temperature. Okay. This is starting point for your XP, right? And then the ratio between, you know that, even this one, we have this way. This is the solid phase. Right? This is the liquid phase. Right? Understand what I'm saying?
yeah, but my question was like, if you draw that point between the boundary of solid and liquid, do you know how many percentage of A is liquid and
Yeah.
how many percentage of
You know, that's what I'm going to say. You know this point, you know this percentage of B, okay? This is the percentage of B in solid. This is the percentage of B in liquid, right? And we have two parts, right? We have two compounds. One is solid, the other is liquid, correct? And then the solid, the number of solid divided by number, or molar of the liquid equals to this length divided by this length. Okay? That means if you have that means for example, this one, we call this length, for example, this length is L solid, this one is called L liquid. Okay? Then NSP that equals to L liquid, LS. Okay? That one called the liver law.
But from this, we cannot tell how many percentage of A is in solid form.
It's reading from here. Just reading from here. So this is the percent. You read the percentage from this point. Let me repeat again. For example, you cool down. You start from this point. Okay. You start cool down to this point. You cool down to this point, and then you're on the boundary, right? But everything is still liquid, correct? And then we'll keep moving. For example, if you keep the solution at this temperature, then we have two components. One is liquid, one is solution. Okay, one is liquid, one is a solid. In a solid, the ratio of xb of the B is reading from this point. This is xb in a solid, and this one is xb in a liquid. Okay, it doesn't vary. It's just we only have one kind of solid and one kind of liquid. How many points? But if you keep moving down, for example, if you keep lowering the temperature, then the ratio or the percentage of the B atoms in both liquid and solid change. Okay, it changed to this point, and it changed to this point. That means the ingredients of both solid and the liquid changes as you change the temperature. How many points? How this happens? You have to cool down very slowly to allow that the atoms to diffuse inward or outward, into or out of the solid, to exchange from solid between the solid and the liquid. You know what I'm saying? But if you cool down very quickly, we don't know the ratio. Okay, it's not in the thermal equilibrium. But as long as you keep in the thermal equilibrium, the percentage of B atoms inside the solution, inside the solid, are reading from this point, and inside the liquid are reading from this point. Okay, we only have these two phases. Okay, it's not random. Got my points? Because you can see that from this one. No matter where you start, eventually you only end up with this point and this point. Right? You know what I'm saying? If you have the starting from this point and then you cool it down, not cool it down, and then gives free energy change, then it just becomes a combination of this point, of this compound and this compound. You only have these two compounds, right? Because of what? Because we simply don't have anything here. We know that it's just a mixture of these two compounds. Have the free energy located on this curve, but this curve itself doesn't represent any kind of compound. Got my points? Did I answer my question? Okay. So this is the length diagram. Then we make the system more complicated. This one in the textbook is called unequal enthalpies mixture. What does that mean? That means for the solid, delta H larger than 0, and for liquid, delta H smaller than 0. That means liquid always stable, but solid probably unstable. Okay. then we have these two curves. And you can see that when we talk about the length diagram, the shape of the curve of the solid and liquid are same, roughly the same, the shape the same. But for that one, not necessary, okay? Because the solid have the positive change of the entropy, at high temperature is more flat, is flatter, right? And for the liquid, it's sharper. Okay, it's sharper. You know what I'm saying? It's probably something like this. Got the points? So they have different curvature. Okay? And then the same thing, but at this stage, it's pretty stable, liquid, okay? But when we cool it down, we know that the liquid curve, the Gibbs free energy of the liquid moves up. Right, moves up. Eventually we have something like this. For example, like this, right? And then we can know that on this end, we start to have some unstable, region. Correct, everybody? Right? And then if I keep moving up, we know that both ends will have some unstable region, right? Both ends will have some unstable region. And then it's defined by this tangent line, and on this end is defined by this tangent line. This is the gap, this is the gap, this is the gap. And in between is liquid, okay? And eventually, if you repeat this process and follow the same principle, we will get something looks like this, okay? Look at this one, this half is just a simple length diagram. Now this one is another length diagram, right? So then combine together, you have something that looks like this. Okay. So basically you have half length here, you have another length here. This is because the curvature of these two Gibbs free energy are different. Okay. Then we can have two tangent lines. Okay. Then we have two regions. Okay. And this one is interesting. This one is liquid. Okay. This one is liquid. And this one is the liquid plus solid. This one is also liquid plus solid. But we know these two solids are different. Correct? These two solid phases are different. Right? And that's the reason instead of, let me redraw it. Redraw it better, no problem. Okay? So this is liquid, we know. And this one we call liquid plus alpha phase. This is the beta phase. Okay? Alpha and beta are two different phases of the solid state, in solid state. Okay? Because we have one unstable region here, we have another unstable region here. Okay? And the other thing is that then we have a tangent point here, we have another tangent point here, right? And this one give one types of this is liquid, this is liquid. We also have one tangent point here, we have another tangent point here, right? So you can see that they have different ratio of the B atoms in the solid phase. Although both of them are solid phase, but the ratio of B atoms are different. That's the reason this one, beta phase, is the B enriched solid phase. Alpha phase is the A atom enriched solid phase. Okay? This is A, this is B. Okay? Got the points? Let's keep cooling down. We know that if we keep cooling down, the liquid just go very high, right? Just go very high. And then we only have the stable solid phase, right? We only have the stable solid phase. This is the solid phase, this is the liquid phase. Correct, everybody? When we keep cooling down, the liquids go moving up or forward further, right? And we have all solid phases are stable here. Correct, everybody? And then remember last time we were talking about when you keep cooling down, because the entropy change of solid is positive, then eventually we will have something like this, right? It's moving up, right? It's from concave to convex. And eventually at the bottom, we will have this miscibility gap, right? This is the miscibility gap, okay? And this one is alpha plus beta, and this one is alpha B rich, and this one is beta B rich. We have something like this. Got the points, everybody? Any questions so far? So far, so good, right? Question?
So it's like this S curve. One time we fix the L liquid phase and we change the S curve.
No,
solid
no,
curve.
you don't need to worry too much about the liquid curve anymore, because the liquid is already above the solid, so liquid is not stable anymore. So if you cool it cooling down, the liquid is still moving up, but we simply don't consider anymore, because liquid phase is not stable anymore, right? So of course, I mean at the beginning, probably, I mean we're saying that we're talking about this one, right? So when you keep cooling down, the solid phase looks like this, right? But the liquid phase moving up further, right? You know what I'm saying? Moving up further. So we still do not need to consider the liquid phase. All right, so let's make the job more complicated. Okay, let's make the job more complicated. We were saying in that case, okay, we were saying that the solid phase is flat, is concave at the beginning, and then the liquid phase is here. Okay, and then after we cool down further, cooling down, and eventually the solid phase become this one, right? But what if before the liquid phase moving above a lot, moving above enough, so that only the solid phase are stable. What if the solid phase itself is not stable, and the liquid phase is here? What will happen? That means what? That means the miscibility gap is so large. Okay? The miscibility gap is so large. It's moving very about. Okay, you know what I'm saying? That means we do not have any stable, I mean, solid solution state. You know what I'm saying? This is the stable solid solution state, right? And then below is the miscibility gap. What if the miscibility gap already show up before the liquid got solidified? Okay? Eventually, we will have this kind of phase diagram. Okay? We just move this up, further move down. Eventually, you have something that looks like this. Okay? This can don't move up further and have cut with this area, and eventually you have something like this. Okay? This is a very straight line. This is strictly straight line. Okay. And then we give the special name of this one. This one is called the eutectic phase diagram. Before we talk about it, I still want to construct that diagram with this kind of Gibbs free energy problem that can illustrate the process better. Like how can we, I mean, establish that one better? Okay. Consider. At high temperature, okay, the solid phase already have the Gibbs free energy in such a way, okay? And then the liquid, something like this, okay? The liquid, something like this, all right? So liquid phase is stable, right? And then, well, let me try to make it more, let me try to exaggerate the change, okay? Like this, the smiling face. And then when you cool it down, we have cross looks like this. Correct, everybody? And then we have one tangent line on this area. We have one tangent line on this area, okay? And then you can see, that's the reason we have this region. Okay, we have this one, this unstable region, this is unstable region. You can see this is a mixture of this one is solid, this one is liquid. Okay? And now this one is what? Is solid, and now this one is liquid. Okay? And you can see on this side is liquid, on this one is solid. Correct, everybody? This is basically a lens, right? This is another lens, right? This is the liquid, okay? This is solid. And of course, this is the beta phase. It's a B enriched phase, right? And this one is A phase. correct? And in between, this part is L plus alpha, this one L plus alpha phase. And this one is L plus beta phase. Correct, everybody? And then we keep moving up. Keep moving up. And we start to build this lens and this lens. Correct, everybody? And the magic point happens here. Okay? The magic point happens here. So we have one arm, the other arm of the liquid, of the solid, okay? And then the liquid ends up with here, okay? And then we can use a single line. The single line will get tangent to all three curves, okay? This tangent, I mean, that means all these three curves, these three bottoms, share the same tangent line. All of them share the same tangent line, okay? And then eventually you will have what? You end up with this point. You end up with this point, okay? You have, on this point, you have the liquid, you have the alpha phase, you have beta phase, okay? See? This one is alpha phase, this one is the liquid phase, this one is beta phase. Correct, everybody? Right? And then, if I keep cooling down, the liquid keep moving up, right? And you will find suddenly the liquid phase is unstable. Everything becomes solid, okay? Just suddenly, everything becomes solid, okay? So that means there's no stable, it suddenly becomes solid, and then there's no stable solid mixture of alpha and beta phase anymore, right? It immediately become two phases. Correct, everybody? So that it immediately got solid, right? That means, because although this is the liquid, this is liquid plus alpha, liquid plus beta, and underneath it suddenly everything becomes solid. Everything becomes solid, okay? That's the reason this is a straight line, okay? There's no curvature anymore, okay? And this one is a mixture, alpha plus beta phase. Because see that in this region, there's no stable state, right? Everything needs to become all unmixed, okay? That's the reason this part is still miscibility gap. Okay? Just because miscibility gap is so high that it's crossed with that kind of liquid plus solid phase, okay? Got the points? Okay, you know how we get it, right? But on this end, it's just a pure beta phase. This is a pure alpha phase. And in between is mixture, okay? This temperature, you know that this happens at a special temperature, right? This special temperature corresponding to when these three bottoms share the same tangent line, right? When they share the same tangent line, we reach this temperature, right? And this temperature, we call it the eutectic temperature, okay? Eutectic temperature. Okay? And in some other places, more specifically, this temperature we call it invariant temperature, because it's only have that only that specific temperature, only at this specific temperature that all phases show up together. Okay, all phases show up together. But you can see in other temperatures only have liquid phase or two-phase mixture, but only at this very specific point, only very specific temperature, all phases show up. Okay? Because it's not dependent on other parameters, it's a single point. We also call it invariant temperature. But because this phase diagram we call it eutectic temperature phase diagram, then the invariable temperature we call it eutectic temperature. Okay? But do you know why we call it eutectic? What's the reason for that? Okay, the reason is like this. Eu is a Greek word. Okay? This means well. Okay? Eutectic means solvable. It means conformal solution. That means they can be well dissolved to each other. Okay? What's the reason for that? Look at this point. If I cool down through this point, we have some mixture, okay? We have some liquid plus solid, and then when we further cool down, everything liquefy. But if you cool down through this very specific point, it's just like a single component. It's melt together and solidify together. Okay? You know what I'm saying? That's the reason people believe this kind of ratio is a well solvable solution. And it can melt together and solidify together. That's the reason we call this one is a eutectic phase diagram. Okay? That's pretty much. Okay? And we have no time to finish. We have another very typical phase diagram. We call it I have no time to discuss that one for this time. The other one, the other phase diagram, different from eutectic, is called paratactic. Okay, we have another phase diagram we call it the paratactic phase diagram. Okay, so the difference between paratactic phase diagram and eutectic phase diagram is like this. For the eutectic, we know that this liquid phase is between these two minimum points of the solid phase, right? But what if the liquid phase bottom is on one side of the solid? Okay, so go back home, try to draw the phase diagram in this condition. Try to draw the phase diagram in this condition, okay? And this phase diagram, we call it, the phase diagram generated by this condition is a paratactic phase diagram, okay? That means if the minimum point of the liquid is between these two bottoms of the solid, it's eutectic. But if it is on one side, it's the paratactic, okay? Do some practice, go back home to draw the phase diagram in this condition. We'll talk about next time. No, not next time. Next time I'm going to review the phase.